Students, welcome to this session on industrial metallurgy. This is session number 29, and this is what we are going to cover. So, we'll talk about hyper-eutectic bismuth cadmium alloys, their equilibrium cooling, and the important microstructures that they show. Well, as we discussed in the last two sessions, based on the eutectic reaction, the bismuth cadmium alloys are of three main classes, and this is the category or the class which is the point of discussion today. The hypereutectic alloys, any bismuth cadmium alloy which contains in excess of 40% cadmium in it. So these are the alloys which are going to be discussed in this particular session. And let's take an example. Okay, again I am showing how does a eutectic reaction go in a bismuth cadmium alloy series. So liquid solution of eutectic composition when present at this, I had earlier also apologized, must be 144 degrees centigrade, the eutectic temperature. So if this liquid solution of this composition, the eutectic composition during cooling is present at the eutectic temperature, this liquid transforms to a mixture of two new solid phases, one being pure bismuth, the other being pure cadmium. Now for your illustration, let's take an alloy of 70% cadmium. Now to discuss its equilibrium cooling, we take this alloy, consider this alloy to be present at a very high temperature TA when this would be in the molten state because it is above its liquidus temperature TB, right? So the microstructure corresponding to point A at temperature TA would be as is shown in this schematic, and we have only one phase present in the system, and that phase is liquid solution with chemical composition 70% cadmium. Since this is the only phase, this is 100% by weight. We proceed with the equilibrium cooling of this alloy. No change in the microstructure takes place till we have reached point B, and point B represents the or signifies the or corresponds to the liquidus temperature of this alloy at which the solidification will start. Now, how do we know what particular phase is going to solidify out of this liquid? See, we are going to enter this region, and this region is liquid plus cadmium. So we can say that as we reach temperature corresponding to point B, pure cadmium will start appearing as a solid phase in the microstructure of this material. And if at point B we wish to see the microstructure, you can see that still bulk is liquid, whose composition is now slightly changed with regards to what it was at a temperature higher than the liquidus temperature. It is 99.99% by weight. And the other characteristic thing that you note is that the solid phase in the form of critical nuclei have appeared. Since I said cadmium is of slightly bluish tinge when it exists in the pure state, just for your easy understanding, I have specifically made this solid phase in blue color. So you have this pure bismuth, and since this is pure bismuth, chemical composition is 100% cadmium, and it has just appeared into the system, so weight is 0.01 weight percentage. Then we say that as the cooling proceeds under equilibrium conditions, more and more of pure cadmium, that is solid phase, will keep on getting formed in the system, and this would form at the expense of decrease in an amount of the liquid phase present in the system. And again at point C, we would be trying to show as to what type of a how has the microstructure changed, or what are the details of the microstructure at a point at a temperature corresponding to point C. And if I show, you see at point C, the first change is that the amount of solid phase has increased, and it has changed its shape from this nuclei to this dendritic shape. So grown nuclei are dendrites. Not only this, the chemical composition of the liquid phase now has further changed and would be given by point G. The chemical composition of the solid phase, because it's pure cadmium, it would remain 100% uh, cadmium only. So you see liquid is now of 52% cadmium. Yeah, earlier it was of 69.9% cadmium, and its weight has further decreased down to 62.5 weight percent. The other phase is pure cadmium. Its weight is 37.5. Now importantly, we have reached a temperature just a fraction above the eutectic temperature of 124 degrees centigrade. So here we would see the maximum amount of pro-eutectic cadmium, primary cadmium present in the alloy. The other important, so one important thing is that now the amount of pro-eutectic or primary cadmium in the which can be seen in the alloy would be corresponding to this temperature. So that is about cadmium. The other important thing is about the liquid solution. The liquid solution that now exists in the material system, in the alloy system, at a temperature slightly above the eutectic temperature. This liquid composition is special, and this is the eutectic composition. So now in the alloy we have liquid solution of eutectic composition, and whatsoever amount of this liquid solution of eutectic composition is present over here, when the alloy after a fractional drop in the temperature would reach the eutectic temperature, this entire liquid will undergo the eutectic reaction. But before that, let's see that what's the microstructure at point, at a temperature corresponding to point D. And this is, you can see that the dendrites have further grown. Students, I should have shown 5 dendrites over here, because there are 5 dendrites which are continuing to be there below the liquidus temperature. So we cannot decrease the number of dendrites now, but it is just for your understanding and demonstration. So you can see that the dendrites have further grown, and now the amount of pro-eutectic cadmium, this should have been cadmium, this is uh, uh, this should have been even more than this. So my apologies again for this. And now the remaining is liquid. So what would happen, no sooner we do further cooling, this entire liquid, which is C of eutectic composition, will transform to this entire liquid will transform to a mixture, to the eutectic mixture, that is eutectic bismuth and eutectic cadmium. So suppose now we have further cooled down the system, we have reached the eutectic temperature, and just below the eutectic temperature at point E, if we are interested in finding out the microstructure, it would look something of this sort. So students, you can see that this eutectic pro-eutectic cadmium, so this should have been this, excuse me, this should have been, I've marked it wrong, this was pure cadmium from 37.5% to 50%. This should have been marked as 50%. The same you can see here, just below the eutectic temperature it's 50%, and remaining 50% is the eutectic mixture, and that was that this 50% of liquid transformed to this 50% of eutectic mixture. But now if somebody asks you that in this 50% eutectic mixture that has got formed, how much is eutectic bismuth and how much is eutectic cadmium, it's very simple. You come to point E, apply inverse lever rule, find out the amounts of bismuth and cadmium. You see this gives you the total bismuth and total cadmium. Now the entire cadmium that you see now in the microstructure of the material at point B, E, is nothing but what you have received because of the eutectic reaction. So this entire cadmium that you see is what you find out over here with the help of this over the entire lever length is eutectic cadmium. So you can find this is 20%, and remaining 30% would be your eutectic bismuth. So you have eutectic bismuth 30%, you have eutectic cadmium 20%, and you have eutectic cadmium, pro-eutectic cadmium, which was already there, 50%. If trickily now, if somebody asks you how many type of phases, how many number of phases are present in your material system? Please don't make that mistake of saying the answer is 3, that one phase is eutectic bismuth, one is eutectic cadmium, the third is eutectic. No, students, the answer to this question is that there are only two types of phases present. One is bismuth, the other is cadmium. The only point to be noted is that there is only one source for the formation of this eutectic cadmium, and this has entirely got formed because of the eutectic reaction. On the contrary, bismuth, this bismuth and this bismuth, right, they are sorry sorry, the only source of bismuth is the eutectic reaction. So this entire bismuth that has got formed in the system is just because of the eutectic reaction which occurred at 144. So bismuth comes from only one source, and its total amount is 30 weight percent. On the contrary, if you see cadmium, this cadmium eutectic and this cadmium do not have even iota of a difference between them. Their chemical composition, physical state, crystal structure, lattice dimensions are the same. So both these, this and this, are the same. The only point of difference is the source from which they have come. See, this pro-eutectic cadmium has come through simple solidification which happened in this range before the eutectic reaction, and this cadmium, eutectic cadmium, has come not through simple solidification but rather isothermally through a reaction called eutectic reaction. So how they have been brought in the system is though different, but in terms of phase they are exactly identical. There is not any difference between them. So how many number of phases present in the system? Two phases, sir. One phase is cadmium, the other phase is bismuth. So I hope you have understood this, and now the time has come that we will revisit that whether this equilibrium diagram that we have constructed with the help of experimental method of thermal analysis, whether this diagram is absolutely correct or not, and if it turns out to be wrong, then what was the reason. Students, thank you for watching this online session.